So I asked Volodya to present his version of this talk because we had a week ago in our satellite meeting Vladimir Yudson giving a similar talk. But as I realized, here very few people, except maybe myself and Ilya, attended that talk, so it's a good opportunity to have it again here.
Okay, thank you. So basically, as you understand, this is the very same work. What I did mostly, I get rid of all devils picture, because hopefully without devils, it is much better. Okay, so this is really the work which fits the scope of this meeting, because somehow this work should have been done, okay, maybe not 50 years ago, but in any time between 50 years ago and now. And something in this direction, of course, was done. So this is mostly well, or maybe not so well for other people, forgotten past than something which looks forward. But at the same time, the mathematical beauty of what I'm going to say was, for me, was fascinating, and I think that maybe I will be able to give you some flavor of that. So basically, it is old canonical one-dimensional Anderson model. So the chain, tight-binding chain, in which the hopping integral is 1, and the on-site energy fluctuates, being distributed according to some distribution. Most of the talk will be concerned with the Gaussian distribution of this variable, but I hope that it is not really, it doesn't really matter for what I will be talking about. And this is the Schrödinger equation that corresponds to this Anderson model. And the question which I will ask mostly is to focus on the difference between the discrete Anderson model, the tight-binding lattice, which characterizes by some lattice constant, and the continuous model in which there is a limit where the lattice constant goes to 0, but the mass of a particle remains finite. So basically, I will be talking about the commensurability effects between the lattice constant and the wavelength, which depends on the energy of the particle. And at some energy, there are commensurability points, for instance, the one where the wavelength is 4 times the lattice constant, 6 times, and so on. And there is another language to characterize these commensurability effects, is to say that let's see which fraction of the states are below the energy at which I consider below the energy E which the particle has. And if I'm in the center of the band, then exactly one half of the this fraction is 1/2, and so one can speak about feeling 1/2. So although this is a non-interacting problem, it is convenient also to introduce the filling factor, so the fraction of states below the given energy, and then this commensurability will be conveniently described by this filling factor, and the commensurability means that the filling factor is a simple fraction, rational number. So this is not something which appeared only now. Of course, for 50 years of the history of Anderson model, much has been done. but to the best of my knowledge, the only thing that was done in this direction was the study of the Lyapunov exponent. So this was done in the work first by Franz Wegner and Capus, and then in an extensive work by Derrida and Gardner. And quite recently, there was some revival of interest to this story, and so there were some number of works in the period of 2000 and 2005. So basically, as I said, the most of results in this concerning the commensurability effect were about the Lyapunov exponent. And the Lyapunov exponent is basically the following. So you start from, you give the boundary conditions, and then you see, you look for the solution of the Schrödinger equation. And this solution usually diverges exponentially. And then if you consider the increment that describes this exponential growth, which is rigorously defined like this, then you find the limit when the number of sites goes to infinity, and this is something like an average exponential increment of this wave function, and for the continuous model, it is known to be 1 over 2L, where L is the elastic scattering mean free path, which depends on energy, and somehow for the continuous model, this is the only significant parameter, because the continuous model obeys so-called one-parameter scaling, and therefore the localization length in all its possible meanings is just inverse Lyapunov exponent for the continuous model.
Yeah, when you say continuous model, you do actually seem to be referring to Gaussian white noise. So there can be other parameters if you have.
Yes, I think so. Yes, yes. When also it is possible to do the limit where you have any distribution, but then you send your if you do the limit that leads to the finite mass of particle in the clean limit, then you will have also some white noise because the on-site energies are uncorrelated at every site, and so you will have a white noise. If it is weak, it will be Gaussian.
Indeed, it's the continuum limit of a.
Okay, good. So then, what will be important for me is the following: that if you have a clean one-dimensional system, then everybody knows that the dispersion relationship is like this. This is a wave number, and this is the energy. Now, when I have disorder, certainly the wave number is no good quantity, and but nevertheless, one can use this relationship as a parameterization for energy. So you take the energy which has full meaning, but it is more convenient to parameterize energy in terms of K, using the same relationship as it was for the clean system. And then, you know, all these things like the Lyapunov exponent, like the elastic scattering length, it will be a function depending on this K, and of course on disorder. This is the variance of fluctuating on-site energies. Now, what was observed in those old works was the following: that let's plot the inverse Lyapunov exponent as a function of this K, and if we have a continuous model, we have something like this, which is inverse square of sine. And when we have the discrete model, then at some energies, there are significant deviation from this continuous model limit. And for instance, the most pronounced deviation is when we take the center of the band, the zero energy, which corresponds to k equal pi over 2, and which corresponds to the filling factor 1/2. And so we see that at that point there is some enhancement of the localization length, or the Lyapunov exponents get smaller. Now, but this is not the only one anomaly. It was also found in the very same work by Derrida and Gardner, that the weaker anomaly happens also when we take the energy -1 or +1 that corresponds to k equal pi over 3 or 2 pi over 3 or to filling factor 1/3. And in this case, we also have some anomaly which, however, is weaker than this, because the deviation from the continuous model is of the order, so the height of this anomaly is of the order of w squared, where the w is a small parameter of the ratio of variance of on-site energies and the Hoping integral. So this is the parameter, the disorder parameter. And so this deviation is of order 1, and this deviation is of order w squared. So this is what was known. Now, in terms of rigorous numbers, the Lyapunov exponent in the center of the band for k equal pi over 2 is given by a ratio of 2 gamma functions times times the disorder strength, and the number is like this. Whereas the continuous model, of course, it gives also 1 over L proportional to the disorder strength, but the number here is is 1/8, and so the difference is about 10% only. So, but important thing is that it is disorder independent. The difference between this and this number and that number, and it is universal. So this is what we know about the Lyapunov exponents in the center of the band anomaly. What we know about the Lyapunov exponent for the filling factor 1/3 is that it is no longer universal. So first of all, as I said, the magnitude of the deviation from the continuous model is proportional to the small disorder parameter, and the width of this Lorentzian deviation is also proportional to w squared, but the sign can be positive or negative. It depends, because, and this is also the result of Derrida and Gardner, because there is the third moment here, and I'm sorry, it looks like this square is not the correct one, because the sign dependent on the sign of the third moment, and when the third moment is equal to 0, for instance, for the Gaussian distribution, then this anomaly simply disappears. Why the anomaly at 1/3 requires asymmetric distribution? This was not actually known, and I do not know it even now. what I'm going to do is to extend this consideration of anomalies for the case for other statistics than the Lyapunov exponents. And why it is interesting? It is interesting for the following reason. As I said, what is the Lyapunov exponent? The Lyapunov exponent is just an exponential increment of the wave function, which you take at arbitrary energy. So you do not require this wave function to be an eigenfunction. So you just look for the solution of the Schrödinger equation at an arbitrary energy. And this solution almost always will exponentially increasing, and the increment is the Lyapunov exponent. So as I said, I can define the localization length as the inverse Lyapunov exponent, saying, well, if I have the localized function in the bulk, then at the border I have the tail of this function, and this is the very same one as this one, so to say, in some not very rigorous consideration. And then I can hope that this tail will be the same information about the localized nature of the wave function as the body of the wave function. But in fact, this is not necessarily true, because and in order to distinguish between the definition of the localization length through the Lyapunov exponent and some other definition which knows about the body of the localized state, I introduced two lengths. One defined through the Lyapunov exponent, and the other one defined through so-called inverse participation ratio. Everybody knows that if we have an eigenfunction this time, which is normalized, then because of the normalization, the typical value of the wave function is 1 over localization radius. So if I raise it to square, it will be 1 of the localization radius square. If I sum, there will be 1 of the localization radius, and if I do the minus first power, so I will get something which tells me how many states are significantly occupied by the wave function. And so this will also be sort of localization radius, but there is a big difference between this one and that one, because this one knows about the tail of the localized function, or even about the function which is not normalized whatsoever, because in order to know this one, I do not have to know. I do not have to take wave functions such that I can normalize them. In order to use this this definition, I have to have an eigenfunction, and it should be normalized. And so this can be defined at any energy, and this can be defined only for eigenfunctions. And then there is a question, the dependence on energy. Is it the same for this one and for that one, or there is a significant difference between them? And we can all reasons to suspect that when we have rational filling factors, when this Lyapunov exponent is anomalous, then these two localization lengths are also different. And this somehow is another word to say that there is no one parameter scaling in the problem. So, but at the points of anomaly, this guy was well studied, at least for principal anomaly and the anomaly in the filling factor 1/3. But this guy was not studied at all. analytically. And so one of the goals of this work is to study such quantity and not only the inverse participation ratio, but the full statistics of psi squared. And this will be the goal. Now, the questions is, which was the motivation, is this one, and then this is basically what we would like to know. Now, how to proceed is more or less known. It is known for a long time, and here I will adopt a way which was developed in particular in the work of Jan Fedorov and Sasha Mirlin, and well described in Sasha Mirlin's review paper. And I will only concentrate on some principal features of that. So basically, in order to find statistics of psi squared, you need to know the moments, and the moments can be extracted from the product of the green function, one advanced and the other one retarded. And in order to extract it, you should do some limiting procedure, which sort of get in order to get rid of the energy denominator, which is in every green function, and extract the wave function. Now, this is a simple exercise to show that this is correct, and then each of green functions can be written down as a path integral, and then depending of what problem are you studying, if it is the quasi-one-dimensional problem, then you use for instance, the supersymmetric sigma model. But if you are studying exactly one-dimensional problem, then the sigma model cannot be rigorously derived, and I think it is not correct simply for that problem when there is only one channel. But in this case, you can use essentially the so-called psi representation, where you represent the green functions in terms of the path integral through the super vectors, and then you deal with these super vectors this way or the other. And this was done, for instance, in our work with Sasha Osipov in 2006, but the result is little different from the one for quasi-one-dimensional situation and the usual sigma model. Basically, the main feature of the result is the following: that in order to compute the moment at a point n, what you have to do, you have to, of course, do the path integral, and you have to integrate over all the points, over the fields which live on all the sides preceding to that, and also over all the sides which side number is bigger than n, and each one can be done using the recursive relation for the so-called generation function phi. And so when I integrate over all psi from the boundary to this point, I get the function psi. When I do the same starting from this boundary to reach this point, I get the same function of the with the base space coordinate like this, where n is the size of the chain. But what is important is that there is a shift. There is a shift in the target space variable. So this is the base space variable, and u and phi are the two target space variables that naturally appear when you consider in the framework of the supersymmetric field theory, but this u and phi can have physical meaning, which you can find looking at the final expression. So you see how does this final expression look like? So if you are looking for psi squared raised to the power m, you have to integrate at the end over two variables, psi and u is raised to the power m. Then there is a cosine of phi raised to the power 2m. So that means that if I would naively say that, well, psi is a product of some envelope function and the oscillating phase factor, psi squared, then the meaning of this variable u is just the envelope function in the psi squared, and phi is just the phase. So what to take home from this slide is that every moment is a bilinear function of some generating function. Each one is found, it has to be found from sort of recursion relation. And now I proceed with this.
Can you go back 1 second? For 1 second. Is there a typo there simply? On
Sorry?
the top. On the top.
Yes, this one.
Yes. On the right, there should be m minus 1.
Yeah, it should be okay. You can
M
write
minus
M
1, the other one, the other part of the green function.
No. The other one is 1. But you can take m and n. It doesn't matter. The only thing is that you have some, free parameters raising this to some power and this to some other power. You may say that this m and this n and m plus n is exactly equal to this power. So here we took, we didn't write unnecessary things, and so we took this equal to be equal to 1 and this equal to m minus 1. Important is that the power of this and that is equal to m. This is the only important thing.
What does z and k depend on in your expression?
What?
What does z and k, on what do they depend? I don't.
D and L.
Z.
Z in the argument of.
Yes.
On the right.
Yeah.
On the
phrase.
The formula is the phrase.
Below,
No,
bottom,
no,
below is the
The
phrase.
last brackets.
To the right.
To the right, yes. Z.
Look, this is again misprint, so it should be U. It should be U. It should be the same.
And the shift k, on what that depends?
The shift is here, and it is shifted by exactly this k, which I defined like energy equal 2 cosine k, and this is something which depends on the energy.
Now, in this derivation of the field theory, which assumptions were made?
What?
There were certain assumptions.
No, there were no assumptions.
There's no assumption.
Up to now, there were no.
Gaussian probably. Gaussian.
No, yes, Gaussian. Gaussian distribution of disorder was an assumption. Right.
So K is just the node counting. The node counting for the wave function.
Node count. Node count.
Yes.
Yes. Okay. So then basically, if we know these moments, then we can find the distribution function of psi, or equivalently, we can find the joint probability distribution of this u and phi. They are connected to each other, and so basically, the main point is to find this function phi. The main thing is to find this one. If I know this one, then I can compute the distribution of psi squared, or I can compute the joint probability distribution of u and phi. This becomes accessible to me. Now, now the main thing in the expression, the main thing about this phi is that it can be found via sort of evolution equation or recursive relation. And this recursive relation, you know, looks symbolically like this. So there is some operator which acts on function phi at a base space point n, produces phi at a base space point n plus 1. But what it also, what is important for me now is that there is a shift by this k, and k it will appear all the time in order to avoid questions is 2 cosine k. Now, so you see, it is not a simple recursive relation because this function and that function are different. They are, one of the arguments is shifted. So what should be done in order to write down something which is a continuous equation? One has to, if k is pi by a rational number, so this is exactly where we are looking for anomalies, then and this function should be periodic with a period of pi, then if you do q iterations, which is q is the denominator, then you may close this equation. And if you, in addition, say that your disorder not only Gaussian but weak, then you expand this evolution operator in powers of your disorder. And to the first approximation in small disorder parameter, what you will have when you do q iterations, you will have a sum of q terms like this, each one is shifted by k with respect to the previous one. So you have L of phi minus k, phi minus 2k, and so on. And this will be the starting point to produce the continuous equation. Now, okay, so I take again this this expression, and what will be important for me, so now this guy and this guy is the same because I use the periodicity, and now I have to know something about this operator. So I know something about this operator because I can derive it, and it contains derivatives with respect to u and phi, the first and the second derivative. But more importantly, it contains sine or cosines of 2 phi and 4 phi. And this is what makes this operator sort of weird, because it is not like the diffusion operator where the derivatives are there but the coefficients are constant. Now, when I sum up q terms like this, so I basically have to do sums of things like that. This comes from sine or cosine of 2 phi, and this comes from sine or cosine of 4 phi. And here there is the textbook identity, that when you do such sum, you always get 0. But when you do such sum, you get 0 for every q but 2. If q is equal to 2, you have a resonance, and this guy gives you the result which depends on phi. And so when I sum q such terms, and I sum it for
This should not be R probably in the right hand side. Because it was R was summation.
Yeah, of course.
Plus phi minus.
Of course, there should be simply,
Phi minus.
yes, this shouldn't be there. Okay. Now, so important thing is that in this sum, which is the evolution operator, for all q but 2, I do not have explicit phi dependent. So they were in every this operator, but not in the sum. And therefore, if I have k, which is everything but pi over 2, and mind you that I did the expansion in the disorder to the lowest order. So if I have all k but pi over 2, then I have a good evolution equation because it doesn't depend explicitly on phi because of this 0 and that 0. And it is well-known equation which arises in the continuous limit. And it has been solved long ago and statistics was found, so there is nothing to do here. But if I have a k equal pi over 2, then I have this explicit dependence on phi, and what comes out is that the evolution equation, which is of the Fokker-Planck type, this evolution equation becomes the second order partial differential equation with respect to u and phi, but with the coefficients which depend explicitly on phi. So what is it? What is this equation? So here there is the evolution in the base space. This is a continuous variable in the base space. And here there are two parts of the operator. So one of them is the same as for continuous limit. And it has the second derivative, and okay, so it's well known. Now, and the other one, it appears only when k is equal pi over 2. And then it looks like this. You know, in these variables which seem to have physical meaning, like u and phi, it looks absolutely terrible. It contains, to the first glance, arbitrary combinations of cosine phi and blah, blah, blah. And the question is, do you believe that this equation is exactly solved? I do not know why, but I believe that it was. And this, you know, this motivation helped us to solve it. But before I show how we solve it, I do the step back, and I give you the generalization of this situation. If you do expansion in the disorder parameter, which is higher than the one I did before, which is higher than the leading order. Now, then the Fokker-Planck equation will look, okay, this is just a symbolic notation, but important is that this operator, okay, it is expanded in powers of small disorder parameter, and this one is what I have just discussed. It contains the regular part and the part which is present only for k equal pi over 2, but it appears that each one of them contains a regular part and the part which is present only at k equal this. So if you take, for instance, the next order in W, then you will have some anomalous part which is present only at k equal 1/3 and 2/3 of pi, and then so on. So actually this mechanism of getting the anomalous terms, it is general. So it is, I demonstrated it for the case of the lowest order, but in fact it is general. Now, how to solve the equation? And now I am considering only pi over 2 principal anomaly. So, okay.
May I just interrupt you for a moment? Just our operator said that somebody has a mobile telephone switched on, and this leads to a strange resonance.
I have a mobile phone
we
which is
hear.
switched on, and I will switch it off right now.
Because it's really disturbing.
No, I have it, so
So if everybody could.
I didn't know that it is.
say it would be helpful. Sorry for this interruption, but it was disturbing.
Yeah, but it is some. I don't know
Like
why
the
does
way
it.
office and one under left.
Maybe. I don't know.
Look, I don't know why it doesn't switch off. It is new one, and
Give it to me. Maybe
Yeah,
it would be
okay.
better because it's further from the source of.
okay, maybe it is because close to the microphone. Okay, good. So I have shown you the equation which looked hopeless, and we wanted to solve it, and we succeeded. So after some change of variables, you switch from u and phi to u is the same, and v like this, and also change a little bit the function. Then you obtain very symmetric equation. So this is the very same equation that was before, with all these cosine and sines taken in apparently arbitrary order, but it was a very well defined order in it, because eventually the equation becomes like this. And this equation actually is very interesting, because in order to write down this equation, I need actually some algebra which is six-dimensional. So first of all, there are gradient terms here, and the gradient terms can be written like d1 squared plus d3 squared, where the d operators defined here. And these d operators actually are the members of the SL2 group, because if you do the commutator of d1 and d3, you obtain d2, and all the three somehow obey the commutation relation like this. So this is the hyperbolic analog of SU2. But there is also this operator here. And in order to be able to describe it, you have to extend your algebra. You have to define B operators, where B3, I don't know why 3 is this one. And then you define B1 and B2, and you find that all of them have nice commutation relationship, and so altogether there is a six-dimensional algebra which does some rotations and translations, in principle it is interesting, starting from here, to uncover the underlying symmetry that helps to solve this equation. This is only six-dimensional algebra, and so I think it is not. It is for an experienced person, it is even easier than what we have done. But we are not so much experienced in the group theory. What we did, we solved this equation straightforwardly. So what we did, we defined again a new function, and the new variables, okay, we guessed it. Psi, which is in initial one, looks like this. And then, to our great pleasure, what happens is that the equation becomes like this, with this totally separated variables, and each of those Hamiltonians, which is one-dimensional, is also of very nice form. It is inverse square with some mixture of inverse of the Coulomb term. And the solution to such equation is well known. It is the Whittaker function. It's a sort of parabolic cylinder, hypergeometric function. But one can even map this onto the oscillator problem. But all of them suffer from one very important important drawback, and this is that each of those operators is actually not Hermitian. And it is not Hermitian because of this singularity at psi equals 0, and because there is no boundary condition which says that your wave function must be 0 at 0. So usually when you consider usual oscillator, so you say, well, your wave function must be something, either wave function or its derivative should be 0 at 0. And that immediately enforces the hermeticity of your operator, and then everything is fine. Discrete spectrum, orthogonal wave functions, and all these type of things. We do not have this boundary condition in this problem. So we have to live with the situation where, in fact, lambda could be complex and continuous. And then we separated the variables, but we have a huge problem because the function psi and the function phi, which I'm looking for, is given by the integral over the whole complex plane of some coefficient times these two functions, which are Whittaker functions, solutions to one-dimensional Hamiltonian. One with lambda and the other with minus lambda, because what we are looking is the zero mode. We are looking the solution to the equation with 0 in the right-hand side, which corresponds to the solution which is independent of the base space coordinate. So this gives you a limit of distribution function in the bulk, so far from the ends. Now, this is because of that is lambda and minus lambda, but what to deal with this? And okay, so the first step is simple. I will not describe it. It is simple. It is based on the fact that this guy depends only on lambda, but not on lambda bar, which is complex conjugated. So it is holomorphic. If this is holomorphic, then you can, in fact, transform. You can get rid of the phase in this lambda and bring all the phase dependence to this C, and then define a new C, which is an integral over the phase of lambda of that C. And this is somehow a rotation of the contour. Of course, you have to watch the conditions at infinity, but if you do so, you can write down the generating function that I was looking for, write down as a one-dimensional integral, but still of some function of which we know only that at lambda goes to 0, it must be constant, nothing else. So then the question is how to fix this function. So we still have a continuum of solutions, but physics seem to tell us that if I'm looking for some distribution of eigenfunctions in an infinite chain somewhere in the bulk of a very long chain, where we believe all functions are localized, then somehow to believe that the boundary condition can matter in this case would be very strange. But if the boundary conditions do not matter, then actually the solution of the zero mode equation should be unique, because this is the only way how to get the solution independent of the boundary conditions. So we have to find some way to fix this C and to find a unique solution. And actually, this was done. The point is the following, is that if I look at this function in this form, where psi is like this and eta is like this, the periodicity is guaranteed in phi. but what is not guaranteed is that your function, as a function of phi, will have cusps like that. So it may be, let's say, at phi equals 0, some cusp, and then another cusp. So this is what is strange. And what we did, we simply required that such cusp do not present. And it is possible to find the solution and solve it when the cusp are not there. So how to do it? The Whittaker functions, they are actually expressed in terms of the hypergeometric, degenerate hypergeometric functions.
So these, I just want to make sure these lambdas are the different types of non-self-adjoint boundary conditions you're integrating over, or what? What does lambda mean here? Does it have to? Is that indexing the boundary condition, or what?
No, this lambda.
Yes.
No, this is just a variable of integration.
Yeah, but it was eigenvalue of your non-Hermitian.
It was an eigenvalue of the one-dimensional operator. It was an eigenvalue.
You have a singularity of 1 over c squared, something like that, right? Which made your solution ill-defined.
Okay, I will return back in order to address the question. So this was the equation to solve.
Okay.
And lambda was an eigenvalue.
Lambda is just the eigenvalue. Fine. So how did you resolve the fact that this is not Hermitian and that you have several possible solutions?
No, but this differential equation, like a differential equation, you don't have to know if it is Hermitian or not. It is well known in the mathematics literature. So if you take the Gradstein and Rizhik, for instance, you will find the general solution to this second order differential equation.
For any lambda.
For any lambda.
For any lambda, but you have more than one, right? I mean, it doesn't uniquely define.
Yes, right. But there is one boundary condition that I have to respect, and this is the boundary condition that as a function of psi, as a function of u, because psi is u times cosine, u can be arbitrarily large.
Yes.
It is not compact.
Yes.
And so I know that this guy eventually has to be distribution function. It has to be normalized, integrated with powers and so on.
Yes.
So it has to decay where u goes to infinity.
Okay.
And this condition
That sets it.
helps you to take one. But
Okay.
One more question.
Yeah, I was going to say that I would expect these eigenfunctions not to be well defined. You start at an arbitrary energy, I mean, take a finite line, you start at an arbitrary, at a given energy, you start at some point and say the origin, you integrate to the right and it grows, you integrate to the left and it grows. Now, to get an eigenfunction, you have to match something that grows from the left and something that grows from the right. But that's only defined for a finite system. If you double the size of your system, you throw that right out because you're no longer growing from the same place. So eigenfunctions are not stable in these kind of problems.
no, you are talking about the base space, or you are talking about the target space. So I have been talking about the target space now. But you are talking about the base space.
But the ambiguity is there. I'm talking about real space. The ambiguity is there in real space, and I suspect.
No, in real space, I'm looking for solution which does not depend on space coordinate whatsoever.
It was iterated from both ends, then to make.
Yeah, so long as you know exactly where the ends are, and but to get an eigenfunction.
No, I'm looking for a solution which in terms of
and that's got to be integrated from both ends.
I'm looking for a solution that behaves like this. If I start from here,
Yeah.
and of course, if I start from there, it is like this.
Yeah, and it won't
And
matter.
I am somewhere here.
The claim is that they won't match. I think
Huh?
the claim is that this will be different costs. But I think in this problem, probably not.
Finite chain I cannot tackle because
Okay, we should talk some more about it. But
Okay,
I
good.
thought quite a lot about this problem.
Good,
and
okay.
I don't think you can do what you're trying to do.
So, okay, so what I have to
Results
do,
are fine.
I have to get rid of such kinks. And where these kinks are hidden? These kinks are hidden in the following. So suppose that my phi is close to 0. Now, then what matters is this function. Now, I look at this function where z should be something like phi squared. And I see that there are two parts in this Whittaker function. One part which is fully regular in z, and the other part which contains the square root. And this square root, in terms of, if I substitute phi squared there, will give me modulus of phi. And the modulus of phi will give me the cusp. But if I, but actually here there are two terms, one like this and the other is complex conjugate. And if I manage to cancel this part in both of these terms, then I win. And this actually is a condition like that, which looks completely hopeless. And that was another point where we were about to give up. Because what it means that for any psi and for any eta, this combination should be, so we should find such function C that this epsilon is simply rotation by 45 degrees, I pi by 4. And now we have to find such C that this guy is 0. So, you know.
The function of psi, of variable psi. So just identically for any psi.
For any psi and any eta. So it is even worse than the first order integral equation, because the first order integral equation requires that it is 0 for any one variable, but here there are two. So this should not hold and looks completely hopeless, but it holds. And it holds because if you open up Grotstein region, you will find the identity number 1 in this book for this hypergeometric function. And if you look what this means for this particular combination of indices, you will see that this means that this guy is equal to that guy, and that means that this combination is exactly equal to that one. And then everything else is very simple, because if I take this C to be the product of two gammas, then I will satisfy this equation. And this is the solution. Now, it is only possible that because of this identity, and this means again that there is some symmetry behind which probably means that there is very simple solution of the problem. But we went somehow a path which was very complicated. Anyway, we have found this solution, and we have shown. Then there is the last step. The last step is to show that this solution is unique, because this is simply something that I guessed again. But one has to show that it is unique. And this can be shown, I will not show it, but it can be shown by showing that, that the general solution is a multiplication of this solution by some entire function. And then if you look at the properties of this entire function, it must be constant because of some asymptotics of the Whittaker function, this and that. So it is simply, like usually it happens in the problems with complex variables, that entire function must be constant. And so this is the final result, which looks not very simple, but nevertheless it is an answer in quadratures, because this is the generating function. Psi and eta are given in terms of the initial variables, and there is one integral over lambda where this gamma is this c is well known. So there is a combination of gamma functions, hypergeometric functions, and one integral. So this is the end of the story. This is the end of the story, and when I found this guy, of course I can compute now moments, I can compute distribution functions and all what I wanted to do, but I didn't yet do it because of the lack of time and because of the complicated integral of the Whittaker functions which are there. So numerically, of course, it is possible to do, but analytically is not. And this is the summary, and this is the main appeal to the audience.
People waiting for